It is a comet of superlatives, the biggest nucleus we've ever seen, an orbit scarred by a mysterious solar event. A bizarre clockwork rhythm of eruptions pointing to a hidden companion. Comet C/2025 R2, SWAN, has challenged our expectations at every turn. But the deepest mystery of all may lie not in its size or its behavior, but in its very essence, in the chemical makeup of its ancient ice. When astronomers used the James Webb Space Telescope to analyze the gas erupting from the comet, they found a composition unlike any comet they had seen before. It was extraordinarily rich in supervolatile ices, like nitrogen and carbon monoxide. This strange chemical recipe is more than just a curiosity. It is a clue, a fingerprint from the place where this object was born. And this fingerprint does not seem to match our solar system. To understand where this comet came from, we must first understand the place where our own comets are born. Our solar system does not end at Pluto or the Kuiper Belt. Far beyond the most distant planets, extending almost halfway to the nearest star, lies the Oort Cloud, named after the Dutch astronomer Jan Oort, who first theorized its existence. This is the final frontier of our solar system. It is an immense spherical shell of trillions of icy bodies, the primordial leftovers from the formation of the sun and planets. These objects were formed in the early solar system, closer to the sun, but were then flung out into these distant, stable orbits by the gravitational influence of the giant planets, primarily Jupiter and Neptune. Here, in the deep freeze of interstellar space, they have remained for 4.5 billion years, perfectly preserved. The Oort Cloud is a ghost realm. We have never seen it directly, but we know it's there. Because every so often, the gravitational nudge of a passing star, or the tides of the Milky Way itself, will dislodge one of these icy bodies, sending it on a journey of millions of years, a long, slow fall towards the sun. These are the long-period comets. They are messengers from the most distant and ancient part of our own home. But what if a visitor came from even farther away? What if an object was not from our Oort Cloud, but from the Oort Cloud of another star, 100 or 1,000 light-years away? For centuries, this was purely theoretical. But in 2017, that theory became a reality. A strange, fast-moving object was detected streaking through our solar system. It was named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. Its path was not the gentle, closed ellipse of an Oort Cloud comet. It was a wide-open hyperbola. It was moving too fast to be bound by our sun's gravity. It was just passing through. Oumuamua was our first confirmed interstellar visitor. Just 2 years later, it happened again. An amateur astronomer discovered a second object on a hyperbolic path. This one, named 2I/Borisov, looked much more like a traditional comet, with a visible coma and tail. The detection of 2 such visitors in just a few years confirmed that our solar system is not isolated. It is constantly being traversed by messengers from other star systems, bits and pieces of alien worlds. This raised a tantalizing question. Could the strange and powerful C/2025 R2, SWAN, be the third? And if so, could its colossal size make it the most important interstellar object ever discovered? To determine if a comet is a native of our solar system or an alien visitor, astronomers must become celestial detectives and analyze the shape of its journey. In our solar system, any object that is gravitationally bound to the sun, from planets to asteroids to comets from the Oort Cloud, travels on a closed path called an ellipse. An ellipse is essentially a stretched circle. No matter how far the object travels, it is destined to one day return to the Sun. Its journey is a repeating, predictable loop. The shape of this ellipse is defined by a single number, its eccentricity, denoted by the letter E, nana. A perfect circle has an eccentricity of 0. As the orbit becomes more stretched, its eccentricity approaches 1. Long-period comets from the Oort Cloud travel on extremely stretched-out ellipses, with eccentricities very close to 1, but always just slightly less than it. An interstellar visitor, however, is not bound by our Sun's gravity. It arrives with too much speed, on a journey that began in another star system. The Sun's gravity will bend its path, but it cannot capture it. This object will follow an open path called a hyperbola. It will swing once around the Sun and then be flung back out into the void, continuing its journey through the galaxy. The key mathematical difference is that a hyperbolic orbit has an eccentricity that is greater than 1. This single number is the deciding factor. If a comet's eccentricity is less than 1, it belongs to us. If it is greater than 1, it is an alien. The difference can be incredibly small, a tiny number buried in the 6th or 7th decimal place, but it is the difference between a returning family member and a visitor from another world. And so, the hunt for the true eccentricity of C/2025 R2, SWAN, became one of the highest priorities in astronomy. As more and more observations of the comet's position were collected, the orbital calculations became more and more precise, but the comet was making it difficult. The strange, non-gravitational push on its orbit, which we explored earlier, added a layer of uncertainty to the calculations. Astronomers had to carefully model and subtract these effects to isolate the pure gravitational path. As the data improved, the number 4e began to settle down. But it settled in the most frustrating and most exciting place possible. The calculated value was something like 1.0002. But with an error bar that still overlapped with a value of less than 1. The evidence was ambiguous. It was right on the razor's edge. The comet was either a native of the most distant reaches of our own Oort Cloud, on an orbit that was just barely bound to our Sun, or it was a very slow-moving interstellar object, on an orbit that was just barely unbound. Based on its path alone, we couldn't be sure. Another piece of evidence was needed to break the tie. This ambiguity left astronomers with two equally extraordinary possibilities. Possibility 1. C/2025 R2, SWAN, is a native of our solar system, but it comes from the absolute outermost edge of the Oort Cloud, a region we know very little about. It would be one of the most primordial and loosely bound objects we have ever seen, a true relic from the solar system's birth. Possibility 2. The comet is indeed an interstellar visitor, but it's a very slow-moving one. It didn't race through our system like Oumuamua. Instead, our Sun's path through the galaxy happened to intersect with the comet's own leisurely journey between the stars. It's the cosmic equivalent of two ships passing slowly in the night. The comet's path, its dynamics, had taken us as far as it could. The shape of its journey had led to a fork in the road with two equally tantalizing destinations. To break the deadlock and determine the comet's true identity, scientists had to look beyond its motion. They had to look at its very substance. They needed to find its chemical fingerprint. Every object in our solar system was born from the same cloud of gas and dust that created our Sun. This means that everything, from the planets to the asteroids to the most distant comets, shares a fundamental chemical heritage. The composition of these objects depends on where in that early disk they formed. Closer to the young, hot Sun, only rock and metal could condense, forming the terrestrial planets like Earth. Farther out, beyond a boundary known as the frost line, it was cold enough for water ice to condense. And even farther out, in the coldest, most distant reaches of the disk, even more volatile gases like carbon monoxide and nitrogen could freeze into solid ice. Comets from our own Oort Cloud are thought to have formed in the region of the giant planets, like Jupiter and Saturn, before being flung out into deep space. Their chemical recipe, therefore, should reflect that origin. They are primarily made of water ice, with smaller amounts of carbon dioxide, carbon monoxide, and other gases mixed in. For decades, by studying hundreds of comets, astronomers have built a clear picture of the standard chemical fingerprint of an object born in our solar system. The ratio of these different ices to water is a key diagnostic tool. To determine if C/2025R2 SWAN was one of ours, astronomers needed to measure its recipe and see if it matched. The James Webb Space Telescope is the perfect tool for this. Its spectrographs can analyze the infrared light from a comet's coma, identifying the unique chemical barcodes of the different gases being released from its nucleus. By measuring the strength of these signatures, scientists can calculate the precise abundance of each type of ice. They pointed Webb at C/2025R2, SWAN, and began to read its chemical story. They found water, as expected. They found carbon dioxide. But as the data for the more volatile gases came in, it became immediately clear that this comet was anything but normal. Its recipe was alien. The spectrum from C/2025R2 SWAN was unlike any comet ever recorded. As we've discussed, comets from our own solar system are dominated by water ice. But in the gas erupting from SWAN, the abundance of carbon monoxide and nitrogen gas was extraordinarily high, in some cases nearly equal to the amount of water vapor. This was the chemical fingerprint of a very, very different environment. To have so much of these super volatile materials preserved, the comet must have formed in a place that was incredibly cold, far colder than the region where our own comets are thought to have formed. It points to an origin in the extreme outer reaches of a protoplanetary disk, a place where temperatures were low enough for nitrogen and carbon monoxide to freeze out in vast quantities. While our solar system has such a region, the specific chemical ratios didn't quite match. The recipe felt alien. It was a powerful piece of evidence, but astronomers needed one more clue to be absolutely certain. They needed to look at the isotopes. Isotopes are different versions of the same chemical element. For example, most hydrogen atoms have just a single proton in their nucleus, but a very small fraction of hydrogen atoms have a proton and a neutron. This heavier version is called deuterium. The ratio of heavy hydrogen, deuterium, to normal hydrogen is a powerful fingerprint of where an object formed. This ratio is thought to be different in every star system, depending on the specific conditions of its parent cloud of gas and dust. For our solar system, we have a very precise measurement of this D to H ratio from studying Earth's oceans and our own comets. Using the James Webb Space Telescope's incredible sensitivity, astronomers were able to measure the D to H ratio in the water vapor of C/2025R2 SWAN S coma. And this was the smoking gun. The ratio was completely different. It did not match the value for our solar system. There was no ambiguity. An object with this isotopic signature could not have formed from the same cloud of gas and dust that created our sun and planets. The case was closed. The comet's chemistry had revealed what its path could only hint at. The evidence was undeniable. The ambiguous orbit, the uniquely volatile chemical recipe, and the alien isotopic fingerprint all pointed to one inescapable conclusion. C/2025R2 SWAN is not from here. It is an interstellar object, a visitor from another star system. This confirmation makes it only the third such object ever detected, and by far the largest and most active. Oumuamua was a small, rocky enigma. 2I/Borisov was a more familiar, but still relatively small, Comet C/2025 R2 SWAN is in a league of its own. It is a true giant, a pristine relic carrying the secrets of its alien birthplace. Its journey, which began millions of years ago in the cold darkness of another solar system, has finally brought it into our light. It is no longer just a comet. It is a messenger. And what a message it brings! The comet's strange chemistry gives us our first detailed look into the building blocks of another planetary system. Its high concentration of nitrogen and carbon monoxide tells us that it likely formed in a protoplanetary disk that was much colder than our own, or in a region of that disk much farther from its star. This suggests that the frost lines for different ices can vary significantly from one star system to another, leading to a huge diversity in the composition of their comets and, by extension, their planets. C/2025 R2 SWAN is the first piece of direct, physical evidence that the chemical recipes for building solar systems are not universal. It's a reminder that the cosmos is more varied and more complex than we can imagine. This single object has opened a new window into the science of comparative planetology, the study of how worlds are born across the galaxy. So if you only remember one thing, it's this. The unique chemical fingerprint of C/2025 R2 SWAN proves it is a messenger from another star, giving us our first glimpse into the chemistry of an alien solar system. Its interstellar origin might explain its strange composition. But as the comet gets closer to our sun, its light is telling a new, confounding story. It is shining with an intensity, a sustained and powerful brightness that even its alien origin and colossal size can't fully explain. Astronomers are now scrambling to understand why this visitor is so incredibly bright.